Okay, let's talk about infinite Cartesian products. So we know how to do a Cartesian product of two sets. You guys remember how we did that? We define A times B was a set of all pairs x comma y such that x belongs to A and y belongs to B. Right? And we actually saw we could do this because this guy belongs to the power set of A union B. Correct, we use the subset axiom to define the Cartesian product of two sets. If you want to define the Cartesian product of four sets, you can probably figure out how to do it. A times B times C times D. It was a set of quadruples x, y, z, w that belong to the power set of A union B union C union D, such that H belongs to A, where this guy over here was defined to be x comma y comma z comma w, right? So we can define Cartesian product between any number of sets we want with the same idea. Now I want to ask about how do we define a Cartesian product between infinitely many sets. So suppose we have sets A sub n, where this set here is a set of all the elements from 0 to, let's say, p to the n minus 1, where p is a prime number. Make the screen a little bit bigger so you can see that. Okay, and we want to define the Cartesian product of all these guys. We want to define A1 times times A2 times A3 times A4 times all the way, all these sets together. What will that look like? What will be an object of this guy look like? Well, I guess you could say, well, it has to be an infinite tuple. Infinite tuple, something that looks like an element from this one, A1 that is below P, and another element A2 that is below P squared, and an element A3 that is below P cubed, and an element A4 below P to the 4, so on and so forth. Infinite tuple. We would like that to be an element of the Cartesian product of these infinitely many guys, right? But first, what is this thing? We haven't, okay, we define extending the definition of pairs to the definition of quadruples by putting pairs together, but infinitely many, that doesn't sound doable. And what is this infinite product of infinitely many things? How do we define this? So I guess what we want is this infinite tuple. We can think of it as a function that, given the number n, outputs A sub n, right? It's a function that goes from n to where? Well, it's not exactly a function, because depending on n, this guy is going to belong to the set A sub n, which changes according to n. So it's not really any function. We don't know what the domain is, the range is. But, well, functions don't need to have a domain. So let's define this concretely. Let's now move on and let's actually define what we mean right here. So here we go. Definition. So first, how are we going to represent all these infinitely many sets? Well, to represent infinitely many sets, we're going to consider a function that for each, in this case, for each n, gives you a set, right? So these A sub n's are a function that, given n, output A sub n. So let H be a function with, let's call it something, the domain as set I, such that for every little I in the set I, h of I is a set. So we have a collection of sets. In the previous case, I was the natural numbers. So for each natural number n, we had a set a sub n. So now we have, we generalize instead of n, which is we have an infinite set I. It doesn't need to be infinite, but could be infinite. The idea is that it's interesting when it's infinite. Such that for every little I, we have a set hi. And so we're assuming it's a set. Wait. So we're assuming that every hi is a set. Didn't we say that everything is a set? Everything is a set. Everything so far that we have in our universe is a set. So this is not needed. Everything is a set. But I wanted to give you the intuition that the h is essentially our function, and you have to think of the objects, the image of h is a collection of sets. And then we're going to define, let's go back to the definition. We define the product, this is a capital A, product for I in I of hi. So it's an infinite Cartesian product of infinitely many things. So this symbol up here is like a big cross product. The same way as when you have plus between two elements, then you define sigma to add, to do an infinite summation of things, or when you have a multiplication between two elements, you define pi for the product of infinitely many things, or when you have, in this case, you have Cartesian product, and we're going to define big Cartesian products to an infinite Cartesian product. So that's what the symbol means. So what is this guy? Let's go back to the definition. This is going to be the set of functions. And what do we want about this f? So essentially, let's draw a little picture right here. What kind of f do we want? We want, so here is, let's say, our h. So here is hi0, hi1, hi2, hi3, right? So here the i's have the elements of I. So in this case, I contains the elements I0, I1, I2, I3. Doesn't need to be countable. I'm just doing countable for the example, but it could be more. And the elements of our products are going to be these functions, and these functions, what they are doing is picking one element from here, f of I0, f of I1, f of I2, and here f of I3. So each element of our Cartesian product is going to be picking one element from each set, and then there are more sets going on as you go that way, right? So what we want is f to be a function, and what do we want about f again? Such that with domain of f equals I, so everything in I is going to be associated to something, and for every little I in I, we need to have the property that f of little I belongs to the set hi. Okay, so elements of our Cartesian product are going to be functions that take each element from the index set. For each element of the index set, pick an element inside the corresponding set, the hi. So we're picking one element from each guy. We need, what do we need? We need to get this guy inside somewhere, right? If you want to apply the subset axiom. So let's put this in a side. Question, where is coming from? I'll let you guys think about this one. It's an interesting question. Where are we taking this f from so that we can define the Cartesian product using the subset axiom? We need to take them from somewhere that we know how to build already. Where are we getting these f's from? Good question for you guys. Okay, so we have a definition for our Cartesian product. So for instance, in the example up here, now our f here, our fn is essentially the element that we say an is the element. A sub n that we put in the list that belongs to an. Okay, so and it goes from the natural numbers and to where? That's the question that we have today. Where is this function going to? And why is that we can take them from somewhere? Okay, so that's an infinite Cartesian product. A trivial observation: if some hi is empty, then the whole product of the hi's is empty, right? Because if one of them has nothing inside, we cannot define the whole function. There are no such functions because just on that spot we cannot choose any value, right? So if you multiply, it's the same as when you multiply. If one of the elements is 0, then the whole multiplication is 0. If you do a Cartesian product between a bunch of things and one of them is empty, you get empty. But what if none of them is empty? Could we get an element? Let's hold that question for a second. Let me ask you another question to you guys. Let me write down here an example. Consider an equivalence relation that we defined in the last video. So on the real numbers. So let R, let's not call it R because we're gonna use the real numbers. Let's E be the following equivalence relation on the real numbers. Again, we don't have the real number yet, but for the sake of the example, we are assuming that we have them. And the relation is the following. So we say that X is related to Y if and only if X minus Y is a rational number. Okay? So two real numbers are the same if and only if the difference between them is a rational number. Okay, so if you move the length between them is a rational number. So what are the sizes of the equivalence classes here? Think about this. It's a good question for you guys. What are the sizes of the equivalence classes? And now what I want is consider I is a set of this is a quotient. I want this to be the quotient R over Q. Okay? So for each equivalence class, I'm going to define a set. And what set I want to define? The same one. So given I in I, so that means I is an equivalence class. We let HI be I. Identity. So that means H of the equivalence class of X under this equivalence relation is just the equivalence class of X under this equivalence relation. So now the question for you guys is find an element of, and let me do this in blue, the infinite Cartesian product for I in I of HI. Okay, so that means I in I is a set of is a quotient, so it's a set of equivalence classes. And for each equivalence class, we are considering the set that corresponds its sets itself. So essentially, we want a function that associates to each equivalence class an element from it, right? But a single element for each equivalence class, we're going to choose one element. Okay, so the whole equivalence class is going to choose. The function is going to map it to a function, an element inside the equivalence class. Okay, so the task for you is to think about how to find an element from it. And okay, so in general, let's go back to the previous comment before. We had that up here, that this observation, that if one of the HIs is empty, then the whole Cartesian product is empty. Now, if none of the HIs is empty, then that means in each one there is at least somebody you can pick, right? So the whole Cartesian product shouldn't be empty. But again, how do you pick an element from each guy in general? And this is actually another version of the axiom of choice, second form. And it says the following: if H is a function with which maps I to a set of sets with H of I different, let's call it now the empty set for all I in the domain of H, then the infinite product of HI's for all the I in the domain of H is non-empty. So that's what another form of the axiom of choice is saying. You want to do an infinite Cartesian product of a bunch of sets HI's, and you know that none of them is empty, and then the claim is that the Cartesian product is not empty. I mean, usually the Cartesian product of things is like much bigger than themselves, right? You're multiplying one by the other, but moreover, if it's infinitely many things, it grows quite a bit. So it sounds kind of silly to say that it's not empty. Of course, it's not going to be empty, but why? I mean, to show that saying that something is not empty means you have to find an element, and to find an element, we need to define it. I mean, so far with the subset axiom, we can only define elements if we have a formula that tells us how to define the set. We can only define sets with a formula, with the first order formula, and the elements of this Cartesian product sometimes they're hard to define because we don't have a formula to choose from them, right? The picture up here, we want to define an element, the Cartesian product, so we need to choose an element from here, an element from here. So to define a single function, a single element in the Cartesian product, we gotta pick an element in each guy, right? So I need a single function, a single element of the Cartesian product consists of one element of each. How do we pick one element of each if we have infinitely many? And if you don't have a rule, sometimes if you have a rule how to define it, each element, then we can use the subset axiom and define it. But just randomly, what does it mean to randomly define? Well, axiom of choice is telling us that we can, that there is a way to choose. It doesn't tell us how we choose. Axiom of choice tells us there is one element in this Cartesian, because non-empty just means there is at least one element. That's all it says. There's at least one element in this Cartesian product that is choosing one element from each HI, one time. Okay, so another question for you guys. What about this axiom of choice question? Is this form equivalent to the other form? Are the two versions of the axiom of choice we've seen so far equivalent? Okay, let you guys think about it. See you next time.